Welcome to Dr. Jed's continuing series on calculus. Section 3.7 from Rogowski is our lesson today. Actually, half our lesson today, because we're going to do it in two parts. It's the chain rule, which is sometimes the dreaded part of calculus, but I don't think it's so bad. First, we're going to review what composition of functions is, because that's necessary for the chain rule. Then we're going to use the formula and do some quick examples of how to use it. Then there's some special forms that help out, that are easier to use. They're very common, and they're easier than the general formula. And then finish with some more examples, including a differential equation. So first off, composition. Composition is f composed with g, which is f of g of x. So f composed with g of x is f. The g of x goes inside. This is the thing that functions can do that numbers cannot. So some examples. E to the x squared, square root of 4x minus 1, and the cosine of 10x plus 2. The thing about each of these is there's something inside. There's an outside function and an inside. If you look here, the f is the outside, and the g is the inside. So what I often do when I write these, so let's break this down. The f is the outside. Now notice it's not f of x, it's f of something, but it's not f of x. So I often write this as f of box, and then g of x. G of x is the inside thing. And inside here you have an x squared. And if I put that in a box, the outside is e to the box. So that means if I put this in the box, I have my function. Now what about this one? The outside, the thing that's happening on the outside is the square root. So this is the square root of whatever. The f of box is the square root of box. G of x then, the inside, is 4x minus 1. And then hopefully you can see on this one, the outside is going to be f of box is the cosine of box. And g of x, the inside, is 10x plus 2. It's not always obvious what's inside and what's not. But usually it is, because if you're going to be using this rule, you need to be breaking the function down. So let's go to the formula and then try these out again. So the formula says the derivative of f of g of x. You'd think maybe it'd be the f prime times g prime, or f prime of g prime, but it's not. It's f prime at g of x times g prime of x, and that part's important. Next lesson, maybe we'll prove this. But right now, let's take a look. If you recall, our f of x, f of box, excuse me, was e to the box. G of x was x squared. So the derivative is going to equal f prime at g of x, that goes inside the box, times g prime of x. So the derivative of e to the something is e to the something. The derivative of e to the box would be e to the box. So I get e to the, and what's in the box? This. So I get e to the x squared times the derivative of g, which is 2x. I'll worry about the niceties of how you write that when we do some longer examples. This one, doing the same idea, but the derivative of the outside is slightly more complicated because what do we have? Square root is actually raising to a half power. So f of box is is box to the 1/2 power. Its derivative would be 1/2 box to the minus 1/2 power. And we can worry about niceties of displaying that when we have longer examples too. So this one, we'll have the derivative of the whole thing will be 1/2. What goes inside? The original function, the g, goes inside to the minus 1/2, but we're not done. There's more, because that's this part. We need to multiply by g prime. And the derivative of, well, the g here is 4x minus 1. The derivative of that is just 4. And then this one, I'll just do it quickly. The derivative here is going to be minus the sine of x, minus the sine of the inside. I said sine of x, and it's not. It's the sine of the inside. times the derivative of the u inside. There you have it. This is how you use the formula. Now, let's take a look at some specific ways it's used. Here's the chain rule again. But two very common things are when you have an external power, when you're raising something to a whole power, we call this the generalized power rule. And the outside is boxed to the n. Here is the derivative of that, n boxed to the n minus 1 times the derivative of g. Likewise, another common form is e to the, sometimes you say e to the stuff. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. Now, aesthetically, we usually put that other stuff right here, the derivative right here, like this. But these are some common ways to do it. You don't necessarily even need to know the general form if you have this or this. Speaking of which, let's do one like each of those. So here's a function, 1 over 3x plus 2, all raised to the 6th. This is the generalized power rule. If you remember, right here, I said it's going to be, pull the power down, 6, the original thing, to the 1 less, so 5, times the derivative of the inside. So let's write all this down. It will be 6, the stuff from before, to the 5th. But that's not enough. We also need, what do we need? We need the derivative of the stuff inside. The derivative of stuff inside, though, that's a quotient. So it's not going to be that easy. I'm going to write it that way, because it's the derivative of that. Excuse me. But the derivative of that is a quotient rule. So let's do it all. Top, bottom. The derivative of a quotient is the derivative of the top. The derivative of 1 is 0 times the bottom minus the derivative of the bottom. The derivative of the bottom here is 3 times the top over the bottom squared. Now, if you look at that top, that's 0 times something, that's just 0. Minus 3 times 1, minus 3. So I have a minus 3 on top. I'm going to combine some things. I've got a 6 multiplied on. Let me rewrite this then. I've got a 6. Let me write that piece. I've got minus 3 over, that's 3x plus 2 quantity squared. And I've got this one. 1 over 3x plus 2 quantity to the 5th. Now, if you're careful with your powers, we can combine this and make it simpler. This 6 and this minus 3, there's no power here, so these are just on the same order, so we can multiply them and get a minus 18. Now, what about other things? We've got a 3x plus 2 squared on the bottom here. And powers on the outside of something apply to the top and bottom. There's a 1 here. 1 to the 5th is just 1. But this to the 5th on the bottom, combined with that, will give us 3x plus 2 to the 7th power. And there you have it. The derivative of 1 over 3x plus 2 all to the 6th power is minus 18 over 3x plus 2 quantity to the 7th power. Let's do another example. This one may look a little unpleasant, but it's e to the x. Remember our generalized rule. The derivative of e to the stuff is e to the stuff times the derivative of that stuff. So the derivative here should be e to the stuff times the derivative of that stuff. That's it. Now, aesthetically, we often put the other one in front, but since they're both e to a power, there's not much reason. Since we're multiplying, we could use rules of exponents and say this is e to the x plus x. Let me write that out so you can see what I mean. That is the same thing. But remember, simplification, the goal is to make it simple to use. Of these two, unless you have a specific reason, I think the top one is almost always going to be the easier one. So I would never do that. But this wasn't very hard, was it? One more. Show that this formula, the square root of 2x minus 1, solves this differential equation. Well, in order to do that, we need to find the derivative. So what is the derivative of that? if y is square root of 2x minus 1, that's 2x minus 1 to the positive 1/2 power. So its derivative, generalized power rule. Bring the half down. Then it's 2x minus 1 to the minus 1/2. But we're not done. It's not just that. We have to multiply by something else. We have to multiply by the derivative of the inside. And the derivative of 2x minus 1 is 2. Now, combine this. Look, there's a half here, times something, times 2. Half times 2 is 1. So finally, let's check it out, see if it works. Y times y prime is 2x minus 1 to the 1/2 times, excuse me, 2x minus 1 to the minus 1/2. Now what does that do? Well, they have the same base, so we can combine the powers. And we get 2x minus 1 to the 0, which is 1. It works. Hopefully that gives you some information about the chain rule, and next time we'll go over it more.